Okay guys, today we are going to be graphing the inverse trig functions. So the little sine -1, cosine -1, etc., etc. It's been a while since we've talked about graphing inverses, so what I have done is picked a couple of algebraic inverses to talk about first, and then we'll get into the actual trig. So remember that when you graph inverses, basically one graph is a reflection of the other graph over the line y equals x. So I'm going to graph these two that I have circled here. F of x equals x cubed plus 2, and g of x equals the cube root of x minus 1. They are inverses, and when I graph them, you get those two shapes. And just for reference, if I graph y equals x, you can see that purple line cuts diagonally through there, and that's the line where those two graphs, the blue one and the green one, are reflected. So these two functions are inverses, and you can see the relationship between the two graphs. So that's what normally happens when you graph a function and its inverse. Now I'm going to move on to the next example. F of x equals x squared and x cubed, and a lot of people would look at those and consider those to be inverses, but look what happens when I graph them. There's x squared, the typical parabolic shape that you're used to, and here's the graph of the square root of x. And that is not a sideways parabola, which you would expect if you reflected that parabola over the line y equals x. In order to get the sideways parabola, you also have to graph negative x, or in other words, you would have to graph plus minus square root of x. Now, graphically speaking, those two graphs are inverted. They are inverses of each other. However, the blue/red graph is not a function. It would fail the vertical line test. If you remember, in order for something to be a function, it cannot intersect the same vertical line more than once. So if you imagine a sideways parabola, any sort of a vertical line passing through there would hit it twice. So these two functions, these two functions are inverses of each other, but the graphs do not look like what you might assume they would look like. To get them to look the way you assume, you actually have to change them so that they're not truly inverses anymore, and the second one would not be a function. So it's a little complicated. When you turn some graphs sideways like that, they would violate the vertical line property, or the vertical line test, and so it would not be a function. That's kind of a big deal, kind of important. Actually, I'm just going to delete those when you get into graphing the inverse trig functions, because trig functions are periodic. Take, for example, the wave that you see here. If I were to invert that and get sort of this weird wave that would look kind of like this, it would wave up and down the y-axis to positive infinity and to negative infinity. Well, that graph violates the vertical line test, so it would actually not be a function. However, inverse sine, inverse cosine, inverse tangent, etc. are said to be functions. So what do they look like? If you can't truly invert the graph, then what are they? So I have them sort of preset over here to the side. You can see on Desmos. Before I do this, I'm going to go to the wrench button here, and I'm actually going to make the y step pi, because when you invert it, you want the y-axis to count by pi and pi over 2, things like that. I'm still in radians, so that's a good thing. Okay, so if I invert this, that's what I get. I don't get an entire wave. I just get a small, tiny little segment or chunk of the wave. Cosine, similarly, is a chunk of the wave up there. Now, tangent, remember what tangent looks like? The inverse of tangent, it's one of those spaghetti shapes. It has been inverted, but it's not all infinitely many of them separated with a bunch of asymptotes. So it's still just a chunk of the graph. This one just happens to go to negative infinity, positive infinity. Inverse cosecant, remember this is the one that looks like parabolas that go up and down and up and down. Well, there, it's sort of half of one, half of another. Now they do go to infinity, but it's still only a portion of the cosecant graph inverted. Secant looks like this. Again, sort of like cosecant, just shifted up a little bit. Cotangent is going to look like a lot like tangent. There it is. So if you compare the two, they're there. But again, remember cotangent, the original graph has infinitely many of those waves up and down, or not waves, the spaghetti shape up and down from negative infinity to positive infinity. When you invert it, there's only one of them. So this is only a portion of the cotangent graph which has been inverted. Now, this has really nothing to do with anything, but when you graph them all at the same time, you get kind of a cool little shape there. I don't know if there's anything significant about that, but I think it looks kind of nifty. So yeah, take that for what it's worth. All right, so we don't need those. I just want you to see that each one has its own distinct shape, and it's not the entire graph sort of turned on its side. It's not. It's just a small portion of the graph turned on its side. Okay, so when it comes to graphing inverse secant, inverse tangent, inverse cotangent, inverse cosine, etc., we're not going to worry about all of the amplitude, period length, phase shift, vertical shift. You really can get into this. So I know this is going to have a vertical shift up to. That's kind of easy. But other things change, and it's not worth a really in-depth analysis and study of all this. We're just going to understand that trig functions have inverses. Those inverses have graphs. The graphs are not a complete inversion of the wave or the infinite number of spaghetti shapes or what have you, or parabola shapes or whatever. They're just little portions of them, and we're going to be comfortable just leaving the rest up to the graphing calculator. So y equals inverse secant of x over 2. So function, the inverses are in the middle column, inverse secant of x over 2. And now we're going to try to do our best to graph those. So here's a point. Now let's see, what is that horizontal line right there? Pi over 2 appears to be a horizontal asymptote, which splits those. What are the coordinates of that point right there? Negative 2 pi. So we've got a shape like this and a shape like that. And that's it. That's the graph. I want you to understand that the asymptote is important, that these 2 points here are critical features, and that your y-axis has to be written in terms of pi now instead of the x-axis because it has been inverted. But that's it. You don't need to figure anything out. You don't need to do any calculations. There's no work to show on this. You're just plotting it or graphing it on Desmos, copying it onto your paper, and we're going to be happy with those results. We'll just call that a success for this type of, new type of school that we're doing right now. All right, inverse tangent of x plus 2. So function inverse tangent of x. Now, there's two ways you could do this. Plus 2 in parentheses, which is not what's on the paper, plus 2 outside of parentheses. So the y-intercept, now that's interesting, 0, 2. Where is 0, 2? Well, it's higher than pi over 2, and it's lower than pi. And can we figure out some asymptotes here? Where does this go? What happens to the y coordinate? Looks like 3.5 something. So a little bit higher than pi. Pi is 3.14. 3.5 is going to be a little higher than that. It's an asymptote. And let's scroll this way. 0.5, 0.4. Looks like somewhere around 0.4. Let's see. Where's 0.4 going to be over? Pi over 2 is 1.57. I don't know. I'll just put a random mark down here. Call that my asymptote. And then just draw my spaghetti shape. Kind of like this. And there it is. Good enough for ballpark graphing. Yeah. Okay, number 6. Y equals inverse cosine of 2x. That's our shape right there. I don't know why that point is still up there. That's weird. Okay, so we need to try to get this duplicated onto our graph paper. Well, first, the y-intercept is sort of an important mark. There's an x-intercept, 0.5 comma 0. There's another endpoint there, which, can I scroll my way? Not really cooperating. 0.5 comma pi. or negative 0.5 comma pi right there. So it looks like I just have a little tiny section of a spaghetti noodle right there. And that's it. That's my graph. No big analysis, no explanation. Yeah, whatever. We'll just call that good. Number 8. Inverse sine x plus 3. Y equals function inverse sine x, and then again out of parentheses plus 3. So it has an intercept at 0, 3, which is slightly below pi. Pi is 3.14, so a little bit below that. Where the endpoint's roughly going to be. Negative 1, negative 1.4. It's going to be a little bit below pi over 2. And oops, that's kind of hard to see. This one is 1 and then just a little bit under 3 pi over 2. So right about there. Make my little curves. And there it is. So I'm thinking this assignment, hopefully not high stress, not a lengthy assignment. It's going to be just easy peasy. That's my wish. That's my hope. All right, number 10. Y equals inverse cosecant x plus 3. And hit the home button so I can see what I'm looking at here. Okay, so it looks like the x-axis is actually an asymptote. We've got y-intercept right there, really close to the the origin. Oops. Let's see, what is this point? Can I tell? Negative 2 comma pi over 2. And then this point is negative 4, negative pi over 2. So I get sort of half of a somewhat parabolic shape here, and another one right there. And that's it. So use your screen, tap and run your finger along it to come up with these coordinates, the way that works. And just try to get as accurate a graph as you can. Number 12, last one, for the notes anyway. Y equals inverse cotangent x, not in parentheses, then we put a minus 1. And again, that's sort of the sideways spaghetti shape. 0 comma 0.5, so where's that going to be? Let's see. So it's about halfway between pi over 2 and 0 is that point right there. 0.6 would be right around there. Can I get some idea of what that asymptote is? What is that line? Negative pi over 3, is that right? That's kind of weird. Yeah, we'll just ballpark it as being right around here. Pi over 3 is going to be less than pi over 2. Where am I? The other asymptote, how high does that get up to? Approximately 2 pi over 3. Yeah, a little bit less than 2 pi over 3, which is, let's call it right around here. Oh, wait, could that be right? Yeah, somewhere around here. And here we go. We got a curve going like this, a curve going like that. And so there it is. Not perfect, but good. It shows that you know how to type this into Desmos. You know that you're looking for certain key points. You understand the overall shapes of them, that they're not repeated to infinity. And that's about all we expect when it comes to graphing inverses right now. We're just not going to get any deeper than this. We may go back and do a little bit more with the other trig functions and graphing, some review. There'll probably be a few of these problems pop up on review, but it's not an analysis where you state the amplitude, state the period length, and on and on and on. So, all right, that's about all we have. So graph these, do your best, submit it through Classroom, and have a great day.